Hello. In this video, I'm going to discuss why enclosures can have a tendency to move after installation. The movement is due to internal pressure, and in the leak repair industry, the phenomenon is known as hydraulicking. This is a concept that is difficult to grasp, so I'm going to break it down into what it is and why it happens so that you can identify scenarios where hydraulicking is a concern. Being able to identify this ahead of time is a useful skill as it will allow you to predict when strong backs are required when you're visiting the leak repair site. And then the necessary measurements can be taken to allow for the strong backs to be installed. I'm going to start by introducing the physics behind hydraulicking, which involves a bit of math, and then I will show you some common examples of where hydraulicking would be a concern. Don't worry, I'm going to try and keep the math light and fast. Let's get into the math and the physics behind hydraulicking. So in order for something to stay put, all the forces acting on that thing have to balance out to zero. That's Newton's first law. If they don't balance out, then you get movement. So in leak repair, we don't have force as an input, instead we have pressure. But pressure is related to force via the formula force equals pressure times area. So inside an enclosure, the pressure is the same everywhere because it's filled with either system fluid or sealant. So the only thing that matters in terms of movement is the net area. If the areas on each side of the enclosure don't match, then that's when hydraulicking will happen. So the way that the net force relates to movement is through the formula net force equals mass times acceleration. So let's try and use this tug-of-war example that I've shown on the screen here on the top right to explain this concept. So here we've got a big guy that's pulling on a rope. You got a small guy on the right-hand side. The big guy is going to pull with more force, and therefore the little guy and the rope, everyone's going to move towards the big guy. It's that same concept with a leak repair enclosure. If you've got a big surface area on one side of the enclosure and a small surface area on the other side, then the enclosure is going to want to move towards the bigger surface area side. So using this, let's take a look at a single bore enclosure as an example. This is an enclosure over a blind flange, which would be quite common. So when I see this enclosure, immediately I can tell you it's going to want to move towards the left. So let's talk about why this is going to happen. So this enclosure has a bore on the right-hand side here, and on the left-hand side, it's just a solid block of plate. So as I mentioned previously, the net force that's acting on this is going to be because there's a difference in pressure area inside the enclosure. So let's take a look at that. So here you can see just the box. Now, pressure fills this entire thing. So on the top surface here, that is identical to the bottom surface. So the enclosure is not going to want to move up or down. It should be balanced, with the exception of gravity, but we won't get into that right now. So what we're interested in finding is the area here on this side of the enclosure. So this is only showing half of the enclosure, but you can see that the pressure area here is 65 inches squared for one half. So times that by 2, you're going to have 130 inches squared acting towards the left. Now, if we measure this side, we have an approximate surface area of 57 inches squared, or about 114 square inches total. So we had 130 inches squared acting towards the left, and we had 114 square inches acting towards the right. So this is not imbalanced. Now, if we assume that there is 100 PSI inside this enclosure, then the side with no bore over here is going to see 13,000 pounds of force acting this way. The side with the bore is going to see 11,400 pounds of force acting this way. So what we're interested in is the difference, because those are going to cancel out. So that's a difference of about 1,600 pounds of force. So you have a net force of 1,600 pounds acting towards the left. So if that's not restrained, that 1,600 pounds is going to force the enclosure towards the blind flange in the direction that I indicated here. It's going to force it like this until it hits something. In this case, it would hit the weld neck, but you'd probably want to restrain it from movement, because if it bumped up against the weld neck, then it could break the seal. So you can think of this like a bottle rocket, where with a bottle rocket, you pressurize it, and then the bore on the bottom of the rocket lets the pressure out, and that forces it up. So we can rotate this like this, and here's your bottle rocket, which is forcing this thing upwards. Now we're going to take a look at a 2-bore enclosure where the enclosure bores are different sizes. Here's a 2-bore enclosure example where hydraulicking will exist. The enclosure is going to want to move down the pipe towards the right-hand side, which is the direction of the smaller bore. So let's take a look at why this phenomenon exists. Similar to the other enclosure that we looked at with a single bore, it has to do with the area inside the box on this side and the area inside the box on this side. So the area here acting inside the box is much bigger than the area over here. A good way to look at this would be to look at it from this view. So you can essentially see the difference is this C shape here following this line all the way around. So that's how much bigger the surface is on this side of the enclosure. Now, that difference in area times by the pressure is going to equal your force that's wanting to launch this enclosure down the line towards the right. Another common example of this is a scenario where you're landing on a flange and then you're landing on a pipe. Let's take a look at that. Here's an enclosure where it lands on a flange and then lands on the pipe past the flange. So it's a 2-bore enclosure. Similar to the reducer enclosure, you have a small bore on this side and a big bore on this side. So the enclosure is going to want to launch to the right. With an enclosure like this, it'd be very common to add a strong back or to maybe tongue into the gap of the flange here. So that would hold it from moving, assuming that the flange gap is big enough, that the tongue is strong enough for the pressure that's acting inside of this enclosure. Here's the key takeaway and the simple math behind the hydraulicking principle. The enclosure is always going to want to move towards the side of the smaller pipe. If it's a single bore enclosure, it's going to want to shift from the side where there is a bore towards the side where there isn't, as you can remember in the case of the full flange enclosure. The actual math to figure out the force that's acting on the box is pi divided by 4 times the OD of the big pipe squared minus the OD of the little pipe squared times the design pressure. That's going to be your force formula. I'm not going to get into how I derived that, but that's ultimately what it works out to be. So why does this all matter? Whenever you're repairing a reducer or covering something with only one bore, like a cap or a drain, you need to check for hydraulicking. If the bore sizes aren't equal, the forces won't be equal, and that means the enclosure will want to slide or even launch itself in the direction of the smaller pipe. To keep it in place, you need some kind of a restraint, usually a strong back. So remember, pressure is always the same inside the enclosure. Force equals pressure times area. And if the bores don't match, the enclosure moves towards the smaller bore. And that's hydraulicking. It's one of the most important checks to make when you're planning or installing an enclosure. Measure both bores, do the quick math, and if they're different, you'll know you need a restraint.